Hi all, this is Ashwin Mutramane. I'm recording this as a part of UCSD TA application process. Today's lecture is about Prim's algorithm to find the minimum cost spanning tree of a graph. So what is a spanning tree? A spanning tree is a subgraph that contains all the vertices of a graph and then there is no cycle formation in it. It means it should have n minus 1 edges. So given this graph here, we can have an example spanning tree for this which will have all the vertices and then there is no cycle formation. So these are the two main conditions. Going to the problem statement, we need to find the minimum cost spanning tree, meaning that the summation of all the weighted edges should be the minimum out of all the possible spanning trees, right? Let us calculate the cost of this, which comes to around 14, and this is not the MST of the given graph. Let us go to. So this is Prim's algorithm to find MST. So for each of the vertex, we have key which keeps track of the minimum cost edge from that particular vertex, and then parent will keep track from which particular vertex this minimum cost edge is coming from, and visited will keep track whether the particular node is visited or not, so that cycle formation will be tracked using this. We can choose any of the starting vertex and then make the key value as 0. Now this is the repeated iteration where we have to check for all the unvisited vertices where the key value is minimum. We are going to mark that as visited, and for all the unvisited adjacent vertices of that particular selected vertex, we need to check if that particular edge that we are considering is lesser than the key value, and then we are going to update these two values as per the algorithm. Finally, construction with these with the table that we have, we are going to construct the MST. Going through the example run, this is the graph, this is the step 1 initialization. We have initialized as per the algorithm. We're going to step 2 where the starting vertex, we are choosing the starting vertex to be A, and then we are going to make the key value to be 0 for that particular vertex. Okay, yes. So step number 3 is the repeated iteration. So what we are going to do is we need to choose from the unvisited vertices which is the key value is minimum. We are going to take that vertex and then make the visited as true. Okay, and then for all the unvisited vertices of A, adjacent vertices of A, we are going to check whether this particular value is minimum than the given key value for that adjacent vertex. Yes, infinity and 2. If you compare these two, for B particular vertex, this is going to be 2, and we need to change the parent to A. Okay, so that we are doing here. And then for other adjacent vertices also we can change it because the value is infinity. So for C and D also the value changes like this. So in the next step, what happens, this becomes visited already in the previous step. Now from the list of unvisited vertices, we are going to check which has the minimum key value, which is B. Now for all the we are going to make this as true. For A is already visited, so for all the unvisited adjacent vertices of this, we're going to check this BD edge, which is 2, and then D value is 3. So now this is obviously minimum, so we are going to update this value as per the algorithm, and then going to the next step. So from all the unvisited vertices here in the iteration 3, now what we're going to check which has the minimum key value. D is having the minimum key value. We're going to make this as true. And then for all the unvisited vertices, B is visited, A is visited. Now for this, adjacent vertices are C and D, which are unvisited, right? So if you check CD, now here the C value is 5, but CD value is 3. So we're going to update this to 3 and then make the parent as D. And also for E value, we're going to update this to 1 and make the parent value as D. Now that is also done. Now going to step iteration 4, what we are going to do is we need to choose which is the minimum value. From here we are going to choose the vertex E and then make the visited as true. And then for all the unvisited vertices, C, is it unvisited? Yes, CE value is 4, but C already has a lesser key 3, so we are not going to update anything. And then D is already visited, so there is nothing to be done in this step. Final iteration 5, right? So there is only one thing that is to be selected, which is C, and then we are going to make this as true. And then there are no unvisited adjacent vertices for this, so we are going to exit step. So now we are going to construct the minimum cost spanning tree using the final step. So this is we have all the vertices present here, and this is the final table that we have, and except for the starting vertex which we chose as A. So for each vertex we are going to construct this particular edge from this to the parent, and then with the key value as the edge weight. So taking B, we have AB weight of 2, and then CD weight of 3, and then DB weight of 2, and then ED weight of 1. So this is how we construct the MST. Calculating the cost, this comes to around 8 for this MST, and this is the minimum cost spanning tree of the given graph. Now going to the complexity analysis, time complexity, we have adjacency matrix approach. For finding the minimum key, we are going to scan all the vertices, and this has to be done for each vertex. So it is order of E squared. And then if we have minimum heap plus adjacency list, we are going to process each edge. So for each each edge we can at the maximum insert total number of vertices. So the heap operation takes log v, so it's going to be e log v, right? And then for space complexity, we have three particular vectors, which is of the size O of v. Adjacency list will be using O of v plus e, and then minimum heap space will be order of v. So the overall space complexity will be big O notation of v plus e. Thank you.